All right, here's some news links that I thought were interesting. Everybody is jumping on the crypto bandwagon. I had the usual boring financial professionals contempt for this, but it looks like people in my attitude have been overruled and the whole world is jumping on crypto and NFTs and all sorts of madness. So since it's happening, I'll cover it extensively in my cryptography class next semester. We will program some blockchains and get them going because it looks like they're here to stay. And there certainly will be jobs helping to program them and find the security flaws and such. So we should cover it just like any other technology. So anyway, now the UK is thinking of making an official Bitcoin. No governments, I think, have made coins that have amounted to anything. China is making one. Maduro tried to make one. I think none of them have gotten anywhere yet. Official government cryptocurrencies. But Britain is talking about doing it. We'll see what comes of that. CodeCov is a place very much like SolarWinds. It is a service used by many other companies, and they got hacked. And I heard on a podcast that what they did was, this is a tool that would pick up your code as you're typing, with like a keylogger, and post it on a system like Git. And it would harvest credentials as you type them. And apparently the way you installed it was by downloading a command line and then executing it. So there's a technique commonly used where you curl to a website and then pipe that to sudo bash to just download a bunch of code and run it. And every time a website does that, a lot of websites install that way, a lot of tools install that way, and they tell you, don't just do it by piping it to bash. You're supposed to read the script and see if it's malicious first, and apparently hackers managed to hack it and add malware to that would steal your credentials. And just like the SolarWinds, it infected many, many companies before people figured out what was happening. So now many companies have been penetrated. They probably don't even know it yet. They don't know how many other pieces of malware and backdoor and other credentials are stolen from them. So, it's a real mess. And we're just beginning to find out how big it is. The same thing's true of SolarWinds. Both of these look like they're going to be years to clean up. And realistically, you're never going to find all the damage, all the backdoors, all the stolen credentials from a really big attack like this. The one thing is the SolarWinds was attributed quite strongly to the government of Russia, I think. This one here does not appear to be a nation-state attack, but it's not that clear. We may learn more as it goes ahead. Anyway. A Tesla just crashed with 2 people in it and killed them. And it caught on fire, and it took them like hours and 30,000 gallons of water to put out the fire, because apparently when a Tesla catches fire, the batteries make some kind of chemical fire that you have to use special extinguishers to put out, and the emergency responders did not have the right equipment or know how to do it. And they said there was nobody in the driver's seat. There was one person in the back seat and one person in the passenger seat. So everybody said this is Tesla's automatic driving failing. But according to Elon Musk, that car did not have the automatic driving feature. So that begs the question, how in the world could somebody be out there riding in the car with nobody in the driver's seat and the car doesn't have automatic driving? So something is not adding up about this, and hopefully we will learn more. But anyway, a couple people got killed, and it is not clear what that means about the safety of Teslas. We got to learn more about what happened there. They put a brick on the gas pedal, I know. Or they thought it was going to automatically drive, got out of the driver's seat, and then found out nobody's driving and it drives right into a tree. I mean, it sounds like something from a Three Stooges movie. That's why I'm having trouble understanding what happened here. Unless they were completely drunk, maybe. But anyway, so Johnson & Johnson is on pause in America because there's a 1 in a million chance of it giving you a very dangerous blood clot. Which the same thing's true of AstraZeneca. And the AstraZeneca and the Johnson & Johnson are similar vaccines. But anyway, Johnson & Johnson, as companies usually do, issued a self-serving, inaccurate claim. They said, all of them cause blood clots. Ours is no different than the others. And everybody is screaming and yelling, that is absolutely not true. Many more doses of Pfizer and Moderna have been given out, and they do not cause this blood clotting thing. So saying they do is just an appalling thing to say when we don't want more vaccine hesitancy in America. And the fact is, all 3 of the American vaccines are very safe, and Pfizer and Moderna don't even have this 1 in a million problem, which is a pretty small problem anyway. But anyway, so Fauci said by Friday we should have a decision about what they're going to do with Johnson & Johnson, and what they'll presumably do is keep using it with like more warnings, or only certain people using it that are less likely to get the blood clots, or some kind of risk mitigation like that. So this has been increasingly coming. Since January 6th made it extremely clear that there are a bunch of violent insurrectionists on the right in America. More and more of them are in law enforcement and in the military. And that's what they say. The Oath Keeper talks about it. This is also some chat logs leaked out from a alt-right group for like Army Rangers and such. So the point is, in case anybody didn't know this, a whole lot of the people that believe that Donald Trump really won the election and really think they need to take like angry military type action to overthrow what they see as the illegitimate democratic government, a lot of those people are in the military, ex-military, in the police, and so on. So it's a real, this is the problem with civil war. You've got people on the other side at high levels in the government. Anyway, so the National Academy of Science, been around for a long time, America's equivalent of the Royal Academy in the UK, has passed a rule a couple of years ago that it's not okay to sexually harass women, and now they're finally enforcing it. There's like 4 famous scientists now that have been known to be like sexual predators for years, and they're pushing them out. I didn't see Tara Wheeler's talk. I forgot and slept through it. I've got other things happening, but I think some students might have seen it. I bet it was good though. Tara Wheeler is very well known. Anyway, so you might see some action there. And Amy Klobuchar, this is something I saw recently. Most of the vaccine misinformation on social media comes from a total of 12 people. It's just 12 people spreading most of the anti-vax stuff. So Amy Klobuchar is trying to get Facebook and Twitter and such to kick off those 12 people. It seems like it would be easy enough to do. They have been claiming they're trying to do something about medical misinformation, but of course they're really not doing much. So anyway, she's trying to push them, and we'll see if she can perhaps even get some action out of them. All right, anyway, so we're up to the official time to start. So here we are at 1:27, and we're down to Windows Structured Exception Handler exploits. So I'm going to talk about the first part of this chapter about Windows overflows, and then demonstrate the SEH exploit. And that's my plan for today. So I got slides here. And, oh, it looks like my, this thing wasn't quite in the right place. Well, anyway, put this one in the right place. My Mac has been giving me a little trouble, so got a few things out of adjustment. Anyway. All right. So we're going to talk about the thread environment block and the processed environment block, and then buffer overflows on the stack, ASLR, and the structured exception handler. And then your book was written so long ago, it's talking about Windows 2003, and I'll talk about the defenses that were added in Server 2008, which is also pretty old, but it gets us up to all the defenses that are relevant even up to Windows 10. So a process that runs in the machine, it runs in a group of threads, and each thread has a thread environment block. And this is officially undocumented, partially documented for later ones. All right. And people have gotten so used to using undocumented thread environment block field. Basically, people have either reverse engineered Windows to figure out how to do it, or the information is leaked out internally from Microsoft, one or the other of these things, or both. But the end result is a lot of programs use manipulating the thread environment block, even though you're not officially supposed to do it. Just like if you use Windows, Microsoft would really like you to use Control Panel to make adjustments, but you can go into regedit and mess with the registry directly if you want to. A similar kind of thing. So the thread environment block has the error, the import address table, startup arguments, and a lot of other information available about a process. So yeah, you can find a whole lot more, but it's just a block of data about the currently running thread. And there are segment registers. Now, these things have been around for a really long time in processors, and the idea was they would point to the start of memory segments that were used for certain purposes. And anyway, they're not used much anymore for the original purpose, but on Windows 32, FS points to the thread environment block. So you'll see it sometimes in assembly instructions referring to something starting with FS. Now, there's a thing called the process environment block, which again, we are not supposed to be messing with as programmers. It's only supposed to be used by Windows internally. And so again, there are data structures here which contain information, and here's what people have. These are the ones that are documented. It tells you whether it's being debugged, the base address of kernel 32 and ntdil, and a few other things here. That's what's going on. These are the places where metadata are stored to sort of do the housekeeping, to keep threads and processes organized. All right. So in a stack-based buffer overflow, which is what we've done previously, you find a string where you're able to write more bytes than were reserved for the use of that string, and then you write so many bytes that you make it all the way to the end of the stack frame. So you overwrite all the variables after it in the current stack frame and get to the return pointer and change it. Now that you've changed the return pointer, the classic technique is you jump to part of the stack you just overwrote, so you jump onto the code you injected. So the code you injected was originally a variable intended to be a string on the stack, and then you run it as executable code. This is all very unsanitary, but that's how it works. All right, so it looks like this. You have some variable like a name 20, but you're able to put in more than 20. So you put in any kind of junk, then you put in your attack with a NOP sled and then an egg, which is the actual payload that does whatever you want, like open a reverse shell. And then you put in enough padding stuff to get to the return value, and you put in the EIP a number that will hit the NOP sled. This means that you must be able to write past the end of a buffer. You must be able to also write all the way to the end of a stack frame and hit the EIP, and you must be able to find an address in this injected code, and you must be able to execute that injected code, which was originally reserved to be storing variables like strings. All right, so that's the plan. Now you can use the structured exception handler too. If you're able to overwrite one of those blocks we talked about that has contained the structured exception handler, then you can change the addresses on a structured exception handler. And then if you trigger an exception by doing something illegal, it will try to use the exception handler to process it, and it will therefore go to an address under your control. And you now have to put an address in the SEH. So you're able to overflow a variable, and somehow you're able to get to the exception registration record, which is the address of a handler. And it's the same thing. Then you have to jump back to some codes. Somewhere you've been able to inject NOPs in an egg. You put that in there. That's what we're going to do. And we'll see it's quite a bit trickier than it should be. Now, there are a lot of defenses that were added entirely to stop all this abuse. One of the powerful ones in Vista was ASLR. So in the early days, before Vista, it would just use memory. The first bit of memory would be used for your operating system, and then for the one program, another program, and another program. So you could pretty much guess where you were in memory. But now, every time you restart the machine, it relaunches these processes and puts them randomly in memory, so you have no idea where you are. That's the idea. This, by the way, is an extraordinarily weak defense. In practice, Microsoft implemented it with perhaps as little as 8 bits of entropy. So there really are not that many different places you could be. And so one simple way to defeat ASLR is to just run your attack about 300 times. And one of those 300 times, it will probably be in the location you expect it to be. But still, that's some degree of mitigation. And depending on your version of Windows, it might be more than 8 bits of entropy. Anyway, so, all right. So we got to use the return value. So here's the game. Now, if we want to overcome address space layout randomization, the name is somewhere in RAM, and I don't know where I am at all. It's on the stack. I inject the code, and then I get to the return value. So now the point is, the ESP, the stack pointer, while I'm in this routine, the stack pointer points onto the stack. So if I could jump ESP, I could hit some locations on the stack, and I have a pretty good chance of hitting the code I want to hit. So what I can do is put in the return value, which points not to my exploit, but to some code inside Windows that has a jump ESP. Now that relies on some part of code already on the box not having ASLR turned on. So this is another very common feature of Microsoft defenses. Every time Microsoft adds a new defense, they put it in their advertising material to say, we've got this defense, and it sounds good. And when you actually look into it, they don't really implement it for all the code. So that's what we're going to do here. All right, and so in old Windows versions, if you wanted to use the exception handler, you could look in EBX, and that would tell you where the exception handler was. So it was possible to find things. And that was a way to leak out information about where you were. But now they clear all registers to prevent that. But the SEH address is available here at ESP+8. So if we can find pop return, we can jump back, and we're going to do this live. All right. So there are frame-based exception handlers. If you have some kind of error, it will then use that particular exception handler, and every thread has a frame-based exception handler. So it looks kind of like this. This is the internal structure. You don't really need to know this to exploit it, but this is what's going on. It's a doubly linked list. You have pointers and forward and backward. Well, yeah, a forward linked list anyway. I have series these things. So it tries the first handler and goes to the code, and then the code either handles the exception or returns some value that says, no, I was not able to handle it. Then it goes to the next one and the next one, and when they all fail, it goes to the operating system error handler, which just pops up a generic box like your program has crashed. So this is what the code looks like. Your exception handler will go in here. It will now, this will cause an exception. This exception handler just prints a message and comes back. A real exception handler would presumably make some attempt to print an informative message or make an entry in the log or do something you'd like to do when an error happens. So in Immunity, you can just view the SEH chain, and this is what happens if you just open Notepad. It has somewhere in NT DIL, there's this one and that one and that one. So Notepad has 3 exception handlers to handle errors inside Notepad, which are in Microsoft's library. All right. So you follow that address in the stack. This one here was D9FECC. So if you go there, you'll see the pointer to the next SEH record, SEH handler. That's the active ingredient. And then there's other things here, another one down here, the sort of thing you'll see. So if you overflow the stack to hit the return address, then you will, of course, alter other variables. So alter the saved EBP and the contents of other variables. So it's entirely possible that you will cause exceptions if you're not careful about it. All right. If we're going to gain control of exception handling, we could use EBP on old versions of Windows, but these aren't even in use or supported much anymore. On later versions, we don't have an easy way to find the exception handler. All right, so an old Windows process, at a crash, EBH would point to it, so you can just write jump EBX, and then it will go to something you control. But in modern Windows processes, the third value points to the exception registration structure. That's when you have a crash. So you need to, instead of finding a command that goes jump EBX, you need to find pop return, and then it will go to your exception handler. And we're going to do this live. You'll see how it looks. All right. So in order to stop these attacks, Microsoft added SEH protections. In Windows 2003 Server, they put in these defenses. They try to make sure that it's valid. They won't let you put exception handlers on the stack anymore. So that'll stop the attack I had in the cartoon up there. If it's in a loaded exe or DIL, maybe. It can be marked as not allowed. And if it has no load configuration directory, then that would be good. So these are some attempt to detect suspicious ones. All right, so here's ways to do it. Abuse an existing handler, use a code and an address outside all modules, or in a module without a so-called load configuration directory. But anyway, let's talk about the defenses added later in the time of Vista, Windows 2008. So here's a normal SEH attack. You have a address and then a handler. And so it goes to this one, then it goes to this one, then it goes to this one, and then it goes to an end marker. So this is a correct SEH that has not been modified. But here, if you have an overflow, then they go in here and change some of this to some other address. And they write in here an address that goes to pop return. So this is a damaged exception handler that's been overridden and has only one value that goes to a pop return. So the point is Microsoft can detect that by checking. So what they did was they added SafeSeh. This creates, at the time of compiling, it figures out what the exception handler addresses should be, and it will only let you use those addresses. So if you try to overwrite this address with an address here that points to say pop return, it will not let that program run. This is a very good defense, but this defense has to be compiled into the program. So if you have an old code that was not compiled with this switch that you run on a modern version of Windows, it won't protect you. You'd have to get an updated version of the program that was compiled with this switch. All right. Now, SEhop is another way to do it. This will, that was SafeSeh. SEhop verifies before you use the exception handler. It just hops through the chain to make sure that the chain is still intact and leads to that value at the end that it should. This is very much like Cisco's check heaps, which Cisco uses on routers. It goes through the list to make sure it's intact. And this one will fail because it's going to have some random data here instead of having the right pointer at the end. So that's the point. The SEhop adds an extra registration record at the end, walks through the whole list, and makes sure that it can still get out the end. And that makes sure the list has not been corrupted. All right. So this is the valid chain, which they can put in something and go to the end. This is the invalid chain that can't reach the end, so it will detect it and not fall for it. There are, all right, so SEhop is enabled by default in servers, but is disabled on client operating systems. This is because, in my opinion, I haven't read an official Microsoft explanation, but servers are important and have a lot of data, and Microsoft expects you to be able to pay for an updated product on the server, but a desktop system, a lot of people want to run old software. So they configure it to be less secure, but to make it easier for you to run old versions of things, which many people want to do. Anyway, you can go in the registry and change this disable exception chain validation record to enable it on a client machine of Windows if you want to. If you do, then when you try to do an SEH exploit, you'll just get this error message in your debugger saying the debug program is unable to process the exception. All right, so let's take a look at some cahoots and then the live demo. So this is 127.8a. That's pretty good. It's 127. That's good. Okay. All right, looks like that's it. Okay, what defense is enabled in servers but disabled in clients? Yep, SEhop, where it verifies the integrity of the chain. All right, what defense cannot protect legacy code? SafeSeh. Make a list of what the allowed values are in the exception handler and not let them be modified to other values. All right, what defense can be enabled individually for each process in Windows 7? And I think also in Windows 10, although I'm not quite sure. Okay, that's SEhop. All right. All right, what exploit method worked on the old versions of Windows? Yep, that was EBX had the address you need to exploit an exception handler. All right, what exploit method defeats ASLR for a stack overflow? I guess so. Yeah, I think jump ESP would have been a better thing to put there, but this is definitely the best of the available choices. Anyway, all right. Where's the register pointing to the thread environment block? Okay, and that's the FS register. Okay, so let me record the winners. All right, that might be initials. I know who that is. I know who that is. Okay, so